Welcome to a screencast on enthalpy of formation and more Hess's law. Let's start by considering the reaction of carbon and oxygen to make carbon monoxide. And this reaction gives off 111 kilojoules of energy when 1 mole of carbon monoxide is formed. Now, carbon monoxide can react with more oxygen to make carbon dioxide, and this reaction, gives off 282.5 kilojoules of energy when 1 mole of carbon dioxide forms. Now note, this is essentially a two-step process for making carbon dioxide from the elements carbon and oxygen. In the first step, carbon and oxygen react to make carbon monoxide, and in the second step, the carbon monoxide made in the first step reacts with more oxygen to make the carbon dioxide. And we can add these two steps, or these two possible reactions, up, and note that the product carbon monoxide of the first reaction cancels out with the reactant carbon monoxide of the second reaction, and then a half mole of oxygen from the first reaction and a half mole of oxygen also as a reactant in the second reaction adds up to a mole of oxygen. And if we add up the two chemical reactions to get our reaction of interest, making carbon dioxide from carbon and oxygen, then we have to add up the enthalpy changes as well. And that gives us the enthalpy change overall for this sum reaction. And we can look at this in a diagram by noting that we can start with carbon and oxygen and end up with carbon dioxide either via having carbon monoxide formed first, which gives off 111 kilojoules, and then carbon dioxide forming next, which gives off 282.5 additional kilojoules, or we could imagine going directly from carbon and oxygen to carbon dioxide, and that process gives off 393.5 kilojoules, and starting with the reactants and ending up with the products, we get the same enthalpy change regardless of if we do this process in 2 steps or 1 step. And this is essentially just a fairly simple example of Hess's law, which we've seen before. Another way of stating Hess's law is if we can do a process in several stepwise processes. So if we can write our process we're interested in as the sum of several steps, then the enthalpy change of the total process, the overall process, is going to be equal to the sum of the enthalpy changes for the various steps. And as noted before, the enthalpy change for a process is directly proportional to the amounts of reactants and products. If we reverse a reaction, then we reverse the sign of the enthalpy change. And if we add reactions together, then we add delta H values in the same way as we added the reactions. And this is a very useful way to be able to determine enthalpy changes for reactions that maybe might be hard to do in practice, but if we can figure out some steps to get there, then we can do this using Hess's law. So let's do an example. This might be demonstrated for you in class, or you might see this at some point. This is the combustion of ethanol. And ethanol you can light on fire. It burns with a very pale blue flame. Or you can put some ethanol mixed with oxygen in a small bottle and spark it. And it undergoes a fairly vigorous combustion reaction, and you see flames come shooting out of the top of the bottle. Well, this is the complete combustion of ethanol that occurs, and you should be able to write the balanced chemical equation for this reaction. And that's what it looks like. Ethanol is C2H5OH. It reacts with oxygen to make carbon dioxide and water, and there's the balanced chemical equation for that reaction. So how do we actually do this? How do we use these reactions that we know the delta H for to determine the reaction that we're interested in finding the delta H for? And the general way to do this is leave yourself some working space, and then write the reaction you're interested in this case, the complete combustion of ethanol. And then maybe draw a line, because we're going to have several reactions we'd like to add up to get this overall reaction. And then, generally speaking, maybe just start from the left and deal with one compound at a time, working your way through with what you need to do, how you need to manipulate these, in this case, 3 equations, to get what you'd want. And here we need ethanol, C2H5OH, as a reactant on the left. And we notice we have one reaction, the third one up above, where we have ethanol as a product. Well, we can make this equation in reverse by flip-flopping the reactants and products. And if we do that, we have to change the sign of the enthalpy change. So essentially, that's like taking this reaction and multiplying the enthalpy change by -1 when we flip-flop the reaction. And that gives us C2H5OH on the left, which we would like, and then carbon, hydrogen, and oxygen on the right, and a delta H of positive 277 kilojoules. Now, next is oxygen, and I would suggest skipping oxygen in terms of manipulating equations, because all 3 equations have O2 in them. But if we deal with carbon dioxide or water, then we have only one equation that has each of those, so let's do those first. So carbon dioxide, we need 2 of them on the right. We look at the first equation, it has 1 carbon dioxide on the right, so it's in the correct orientation, but we're going to need to double everything. So that equation becomes 2 carbons plus 2 oxygens makes 2 CO2s, and the delta H is 2 times -393.5 kilojoules, or -787 kilojoules. And then the water, we need 3 waters as a product, or on the right. The second equation has water as a product, but only 1. So we're going to need to take that second equation and triple it. When we triple everything, we get 3H2 plus 3 halves O2 makes 3H2O, and the delta H is 3 times -285.8 kilojoules. Now, we hope these 3 equations are going to add up to the reaction of interest, and if so, then we just add up the delta H's. But we're going to need to go through the process and make sure. So 2 carbons cancels 2 carbons. Carbons on the left in the first equation, carbons on the right in the second. Now we have a half oxygen on the right in the third equation, and 3 halves oxygen on the left in the second equation, and subtracting a half oxygen from both sides leaves us with no oxygen on the right, and 1 oxygen molecule, 1 mole of that, on the left. And then we note that we can also cancel out hydrogen, 3 moles of each on the left and right respectively. And then we're left with ethanol, C2H5OH. 2 plus 1 gives us 3 moles of O2 on the left, and then 2 CO2s and 3 H2Os on the right. So everything works properly. And then we add our delta H's because we added our reactions, and we get a delta H of -1367.4 kilojoules for the complete combustion of ethanol. Okay, now an important thing to note with this is in the reactions that we used to add up after manipulating to get the complete combustion of ethanol reaction enthalpy, in each case we have a compound that was formed from the elements that make up that compound starting in their standard states. And this type of reaction, or the delta H for this type of reaction, is what is known as the standard enthalpy of formation, and we symbolize it by delta H sub F, where the F stands for formation and the superscript 0 is for standard conditions. And this is for 1 mole of compound. So how we would interpret this is we'd say the standard enthalpy of formation of carbon dioxide is -393.5 kilojoules, because to form 1 mole of CO2 from its constituent elements, carbon and oxygen, gives off 393.5 kilojoules for 1 mole of CO2 formed. And then similarly for water and for ethanol. Okay, so let's note that for the reaction that we just did, using Hess's law, we manipulated 3 reaction equations to get the reaction equation of interest and then added up their delta H's. What we actually did was we took the delta H of formation of CO2 and multiplied it by 2. And we took the delta H of formation of H2O and multiplied it by 3. And then we subtracted the delta H of formation of ethanol, C2H5OH. And then in this case, the delta H of formation of oxygen is not really relevant because that's 0. Forming oxygen from oxygen requires no energy or no enthalpy. So we could write this in the following manner. 2 times the delta H of formation of CO2 plus 3 times the delta H of formation of H2O minus the delta H of formation of ethanol, and then minus 3 times the delta H of formation of oxygen. Another way to put this is to find the delta H of reaction for our overall reaction. What we did was we took the delta H of formation of each product, multiplied it by its stoichiometric coefficient, and then added those up. And then we took the delta H of formation of each reactant and multiplied those by their stoichiometric coefficients and subtracted those. And it turns out this is completely general. We can apply this to any chemical reaction. And the way we write this is we say that the delta H of delta H, or the enthalpy change for the reaction, is the sum of the stoichiometric coefficients times the delta H of formation of the products minus the sum times the stoichiometric coefficients times the delta H of formation of the reactants. And this is very useful because there are tables and tables and tables of standard enthalpies of formation of pretty much any compound you're interested in. So if we have a chemical reaction for which we'd like to find the delta H, we can generally just go to the tables and apply our formula. Now, a couple things that are important to note. One is standard enthalpies of formation, as just noted, are found in tables, so we can usually look them up. They are very specific. For example, the delta H of formation of H2O gas and the delta H of formation of H2O liquid are not exactly the same. So we have to be very careful about phases and getting the exact substances right. And then the other thing is that standard enthalpies of formation of an element in its most stable or standard form is 0. So let's give this a try with the following reaction. Ammonia reacts with oxygen gas, nitrogen monoxide, and steam are produced. So let's write the balanced equation. Let's calculate the enthalpy change using delta H's of formation and standard enthalpies of formation. And then, given certain amounts of our reactants, how much heat is produced or absorbed. And let's take these one at a time. First of all, the balanced equation. Ammonia is NH3, oxygen is O2, nitrogen monoxide is NO, and steam is H2O. And all of these are gases. Now to balance, we do the usual thing and fill in the appropriate coefficients. And it's 4 to 5 to 4 to 6 for our stoichiometry. Now that we have the reaction equation, let's use delta H of formation, or enthalpy of formation values, to calculate the energy change for this reaction. And of course we need to look up standard enthalpies of formation. For ammonia, it's negative 46.1 kilojoules. For nitrogen monoxide, also known as nitric oxide, it's 90.2 kilojoules. For water as gas, or steam, it's negative 241.0 kilojoules. And oxygen gas is that's the element in its standard state, so its delta H of formation is 0. So we plug into our formula. Delta H of the reaction is 4 times the delta H of NO, or 4 times 90.2 kilojoules, plus 6 times the delta H of formation of H2O, or 6 times negative 241.8 kilojoules, and then minus 4 times the delta H of formation of ammonia, which is minus 46.1 kilojoules, and also minus 5 times the delta H of formation of oxygen, which is 0. And we plug all that stuff in and get negative 905.6 kilojoules as the enthalpy change for this overall reaction. And if we can look up the values we're interested in the tables, then this is a pretty straightforward plug and chug process. Okay, now how about a quantitative aspect involving amounts of ammonia and oxygen, our two reactants? And this should be fairly straightforward to do. We have 34 grams of ammonia. If you figure out its molar mass and convert to moles, you should determine that that's 2.00 moles of NH3. And if you do the same thing with oxygen gas, you should find that that's 2 moles, 2.00 moles of O2. And now we note that since 4 moles of NH3 requires 5 moles of O2, if we have 2 moles of each reactant, then we are going to have a limiting amount of oxygen, because 2 moles of NH3 would require 2.5 moles of O2, so we're going to run out of O2. That's our limiting reactant. And then to determine the amount of heat produced, we of course start with our limiting reactant, 2 moles of O2, and then we note that we just figured out that 905.6 kilojoules of energy or heat is given off when 5 moles of O2 react, so that's our conversion factor. And then that calculation gives us negative 362.2 kilojoules of energy or enthalpy or heat given off when that amount of ammonia and those amounts of ammonia and oxygen react. And that is it for enthalpy of formation and more Hess's law.